don't know if you can hear me. It's clear? Okay. Welcome to the workshop on survival analysis. I would like to introduce our main resource person, Professor L.Jeyaseelan. He's the professor and head of biostatistics, now retired. And he was the senior member of the clinical epidemiology unit also, which running this workshop. Right now, sir is the professor. He's working in Dubai in the MBRU University as a professor of biostatistics. Thank you very much, sir, for taking this class. From 91 onwards, 1991, when the clinical epidemiology unit was instituted, he has been taking research workshops and all over people from India, Southeast Asia have come to run workshops. And sir has done in many Southeast Asian countries also. He has been invited to run workshops. Today's workshop, as you know, is survival analysis. And increasingly, a lot of papers from CMC also are coming, cohort studies, short cohort, long cohorts are coming. So we thought it's very useful to run this workshop. But at the outset, I want to say this is an introduction to survival analysis. If you want to learn more deeper things than what is being taught today, you may contact Dr. Jeyaseelan.
This question this is, let us understand the basics of the survival analysis. What is different in survival analysis as compared to other analysis? Say, for example, when you analyze a 2x2 table data, we use chi-square statistics. When you have compared two means, you use t-test and so on. When you have outcome variable which is continuous, say for example BMI, who is overweight, whatever, these are all dependent variable which is well defined, follows normal, continuous, and so on. So, how does the survival analysis differ from that other analysis? Why should we understand this? Okay, this is a very simple concept. The survival analysis has two outputs. You need to understand that there is a time and there is an event attached to the time. So when I die, it says yes, he is dead. And I don't die because you finish your studies in 5 years' time. Okay? So everyone is censored. So that means you finish your time, you finish your study. So therefore, he is not dead, but he is still alive. But I am finishing my study. How do we handle it? So he was followed up for 5 years. There is a follow-up time, there is a death time, and there is an event. There is an event whether he is alive or dead or censored and so on. So therefore, if you see how do we handle the two events? One is time, which is a continuous variable. Other one is bivariate, trivariate. Connecting these two is a big challenge. The big challenge what they had was how do we deal with the censoring data? What I said the censoring data. End of 5 years that you finish your study, I'm not here to do a study for 10 years, 15 years, and so on. Therefore, how do we handle it? So all the subjects who are alive and it's called censored. Okay, last of all is called censored. This is the detailed involvement in the survival analysis caused some kind of confusion earlier in developing software, developing estimating the probabilities, etc. So therefore, we will see how are we going to handle this. SPSS is a very simple, easy software to use and very well sophisticated in terms of displaying output. We should be able to. The first exercises which I am going to tell you is that understand the basic concepts of survival analysis. How do we organize the data? Therefore, it is easy to analyze. Okay. So therefore, whenever you say survival analysis, which deals with time and there is an event attached to time. This patient was followed for 5 years and he passed away. That is an event attached to it. There's another patient who was followed for 5 years and he is still alive. So this is censored. Do you understand the difference? So therefore, we need to be careful about this. So therefore, here the ANOVA, t-test, chi-square test will not work. Okay. Now, this is, so therefore, you have the start of the study and there is a survival time and there is an event attached to it. Okay. So the event could be death, disease relapse, recovery, failure, etc. It doesn't have to be only death, relapse. Okay, you can define what is your event. And see here, so therefore, time in remission is your time variable. Disease-free cohort, so time until he develops a disease is the time. And how do we define our time? Because you have to define and the time and the event attached to the time. So therefore, this is the schematic concept of survival analysis. Study starts, followed up, study ends. Still the patients are surviving. So therefore, he is called everybody is censored who are alive is censored at 5 years or 10 years. So that is something which is difficult to analyze those days. Now it is very easy to handle this kind of information. So therefore, when you say mortality and censoring, there are two events. Mortality, who died and who was censored. That is the event. And there is a duration attached to it. That is all we have. Okay. The censoring occurs, no event. So you finish your study because funding agency gave you money for 5 years and last follow. You don't know where is he now and withdrawn from the study. Okay. And so this is important. Let us look at this data. Subject A, if I'm going fast, please stop me. So I'll go slowly. This is a very basic concept. Subject A was followed up for 5 years. And he died at the end of the 5 years. The X indicates that he died. Okay. Subject B followed up for 12 years and study ended. Therefore, he is censored. Okay. And C came in between. Okay, this is the reality. So you recruit patients in a prospective study. So there's a period called recruitment period for 1 year or 6 months. As and when they come, they include that and follow them up. So there are open-ended studies. As and when they come, you follow them up in HIV, AIDS, etc. So therefore, then he contributed 3.5 years, and we don't know where is he now. Withdrawn from the study. So another guy started at the 4th year or whatever, and he contributed 8 years and study ended. Next guy contributed 6 years and last for follow. Okay. Now, the last guy contributed 3.5 years and he died. So therefore, there are 2 deaths in the study and 2 withdrawn from the study and 2 cases where the study ended. So except the 2 who died, all others were censored. So you have a bivariate outcome, which is mortality or censored, attached with the time. The first guy died at the end of 5 years. His time is 5 years and his status is died. Okay. Now, this is what I rearranged everything. This is what my data is. So survival time 5 years. I put a code as failed or died 1. Otherwise, it is 0. Is that okay? Do you understand this? So this is how you need to organize your data. Now, any question? Now, you would ask a question. Who is this person A? Is it male or female? How old is he? And has he had a family history of diabetes or hypertension, a baseline risk characteristics, etc.? You can attach like this. Then it becomes a big data. These are all covariates, risk factors. Do you understand? My main ingredient in survival analysis, what is my time and what is the status that is attached to the time? If you are able to organize this, the 90% of the work is done. Is that okay? Yes.
What if the loss to follow-up was because of death? So should not censored be considered like failed? I mean, some of these censored ones which are lost to follow-up or withdrawing, if we know he's alive and withdrawn, it's a different thing. But it's possible that he may be dead.
We don't know. We don't assume anything. We say when you say withdrawn, that is the time I know him. He was with us. After that, we don't know. So therefore, at that for 3 years or 3.5 years, here say for example, this guy, 3.5 years, I know him, he was alive, and after that, we don't know, sense it. You say 3.5 is the last time you met with him. After that, you don't know. Okay.
The error in assumption, safer to assume the bad event rather than.
No, we don't do that. So I'll tell you, the probability of survival. I have followed up 10 patients. At the end of 5 years, one died. So 1 out of 10 is the probability of survival for 10 years or 5 years. Now, what is 10? I know 10 people to begin with. At the end of 5 years, 10 are with me. I know them, they are alive, therefore 1 out of 10. Now, if 2 or 3 fellows have left the study, not there, I cannot assume that they are alive or dead. I cannot put 10 in the denominator. That is what I'm going to teach you. This is, we just remove them. Okay, from the denominators. As you relieve them from the denominator becomes smaller and smaller, and so on and so forth. So there is no scope for any assumption. That if you do it in your methodology and correct it. So therefore, this is just introducing the notations. When you see here, the capital S of T, which tells you this is survival, probability, cumulative probability of survival. What do you mean by cumulative probability of survival? The surgeons will ask you the question, what is the probability of survival at the end of 5 years if I do a breast cancer surgery? Okay. So therefore, it's a cumulative probability. End of 5 years, what is the probability of survival? It's not how many died, how many is expected to die at that time of 5 years. It is end of 5 years, my say 60% of the patients will survive, 70% of the patients will survive, and so on. That is called capital S of T. Capital means cumulative. S means survive. Okay. The time you specify, 5 years or 10 years, and so on. This is the capital F is the opposite of that. Failure is denoted as F. So therefore, if I say failure, if I calculate how many died at that particular point in time, the complement is 7. Is that clear? S and F notations. Okay. So you always ask the question, what is the probability of capital T, just the notation, but you say small t, you put a value, 5 year or 10 year, you write it. So this is what a simple equation that we say that number of patients surviving longer than T, that is how greater than 5 years. My question is at 5 years and total number of patients. It's a simple calculation. Every time there is a failure, at 1 year how many failed, 2 year how many failed, and so on, that we calculated. Okay, that is what I'm going to introduce. You see here your survival curve. When you draw survival curve, it's like a step function. What does it mean? Over a period of time, everybody is expected to die. Okay. So, but when you start the study, everyone is alive, 100%. Day 0 of the study, the probability of survival is 100%. Over time, it is coming down. You lose the patients, or the patients are leaving the study. The denominator becomes smaller and smaller. Because as I said, censored means you remove them from the denominator. Okay. There are 2 ways the denominator becomes thinner, because either most of the patients are dying or most of the patients are leaving the study. That something has to be examined. Okay. There's another function called hazard function. Hazard is not risk. In statistics, risk is the probability of getting disease. Hazard is not the risk. Hazard is the instantaneous probability of dying in a small time scale, small interval. The time scale could be 1 week, 1 month, 1 year. So this is a rate, and therefore doesn't fit into the probability concept. Okay, rate is not 0 to 1. It can be more than 1. So please remember this. As you change the time frame, the risk hazard will change. Hazard is a very important concept that has been used in survival analysis. We are going to use hazard very much. Please remember, when I say risk, I mean to say probability of getting a disease, probability of dying, and so on. So when I say hazard, hazard is not the probability, hazard is the rate at which people are dying, patients are dying in a particular interval. Say, for example, this is 4.6 deaths per day. So this is hazard. So this is like a speed at which patients are dying and so on. Not a probability, but a rate. So therefore, the probability of dying at a particular interval may be same. Okay. Each time point, the probability of dying is same. But when you change the time frame, what is the rate per day, what is the rate per week, and so on, the rate changes. Because as you change the time frame, the rate will change. So therefore, what we wanted to tell you is the rate is the function of time, but not the probability. Okay, please remember that. So this is to demonstrate, therefore, the rate, as time increases, rate changes. Okay, and this you would have seen that this is a very important concept. For an example here, and after the surgery, the risk is very high, and as they recover from the surgery, the probability, the hazard of dying is lower over time. Okay, there's a trend. Now, similarly, the various this. Why should I show you this? This is when you take Cox proportional hazard model, he developed the model based on the hazard concept. Okay, let us look at his theory. It's a very important concept that which we are looking at. Now, so therefore, if you look at it, that over time the hazard of dying is increasing, therefore, it is an inverse of the survival functions. Over time, survival function comes down. Probability of surviving is becoming lower. On the other hand, over time, the hazard function is increasing. Is that right? Approximately. Now, how do I define or present the probability of survival over a period of time? So the Kaplan Meier, so they have come out with a new concept. So this to characterize the distribution of time to event, the survival time. And this is a summary. How do I summarize? I have followed up the patients for 5 years. How do I put it in some statistics? That is, what kind of statistics do we use? And at the same time, it take care of the sensory. Okay, it's a non-parametric approach and applicable to small, moderate, and large sample data. I remember I was given a data many years ago that there's studies about relapse in leprosy. What is relapse in leprosy? It's a very, very rare event in SAID. So Dr. JP and the nephrologists from government, Salem, they followed up 20,000 subjects, 20,000 leprosy patients in these areas, and see how many of them are going to develop a relapse, have to have a relapse. So what kind of analysis? So each patient was followed up, you have the relapse time, otherwise the follow-up time, and you have to do the analysis. Okay. Now, let's see. Now, this is a question, how am I going to present this data? Summarize and present this data. It's a very rare situation. And so this is, see here. So this means the large samples. 20,000 is very sample. The hospital setting, you deal with the 20 patients, 30 patients, or 200 patients, and so on. So what kind of analysis we should do? Okay. And let us look at this. What is P1? Probability of surviving for at least 1 day after transplant. Transplant is the interest of study. What is the probability of surviving? So day 1, how many are alive and how many I started off with? That is called the probability of surviving. Okay, but when you come to day 2, please remember, this is called a conditional probability of surviving second day after having survived the first day. So the first time when we calculated day 1, I started out with 100 patients at day 1. Therefore, 100 is my denominator. But when it comes to day 2, it is not 100. It is conditional on that you are surviving on day 2. For those who survived day 1 and they are with me on day 2, that should be the denominator. Do you understand this? So this is very important. That is why it is called a conditional problem. So therefore, the people should have survived day 1 to survive day 2. So this is, you extend this concept. When you go to day 3, they should have survived day 2 to survive day 3. So systematically you calculate the probability and plot this graph. Okay. This is something, there's a definition. So the number of patients followed for at least t minus 1 days also survived at day t, that is yours. Day 2, how many survived? Of the people who survived day minus 1, the t minus 1, the first day 1. Okay. So if that is the case, you can see this theoretically. To survive, see here, P2, probability of surviving day 2 is conditional probability, which is, when you say conditional, you should have multiplied it with this, the probability of dying and surviving in day 1, because that is conditioned to the day 1. They should have survived, and so on and so forth. So when you do this one, this becomes this part. When you ask the question, what is the survival probability at day 7? That how many, what is the probability at survival probability day 6, and then the day 7 probability. So this is how we calculate it. Now we'll do this small exercise. If we have a pen and pencil, just see here. I started off with so many patients. Say 2, 4, 6, 8, 9 patients. The plus sign indicates that they are censored. I don't know whether they're alive or dead, but that day 4, I know that he was with me. That is all. After that, I have no idea. That is indicated by plus sign. That means censored. Okay. So I started off with the 10 subjects on day 1. How many died at day 3? This is time. This is time. 1 patient died at day 3. What is the probability of survival in the data at day 3? 9 patients are surviving day 3. Is that right? Out of 10. I started out with the 10. Because the probability is 90%. So you would say that probability of surviving at day 3 is 90%. That's okay. Then do you have day 4 that someone left the study? 5.7 day that from the hospital he ran away or whatever. Otherwise, why it is 5.7? I don't understand. That he is not there. And day 6.5, someone died. Okay. How many died? 2 died. Now, let us look at this. How do I calculate this probability? How many are available with me up to 6.5 days? 1 died here and 2 people left the study. I started off with this 10, therefore 10 minus 3, so 7. 7 are available with me on day 6.5, but and that particular day, how many died? 2 died. Okay. How many are surviving out of 7? 5 surviving. So the probability of survival is 5 out of 7. Is that right? Very simple calculation. What is conditional? Because these 5 people or these 7 people have survived prior to the time point. Therefore, that prior time point probability has to be multiplied. Do you remember I said P1 into P2 and so on. This is a conditional probability that to survive 6.5 days, they should have survived before. So therefore, you multiply this, that gives you the capital X of T. What happens over time? The probability is coming down slowly. Okay. Now, if you look at why the probability is coming down, the two questions should be asked. Are patients dying much faster, or patients are leaving much faster? I still remember the first study in 2005 data from Tamram Hospital on HIV. We did the analysis. It's a very big hospital dealing with, those days, 1.5 million, 15 lakh patients visited in a year to the hospital from Tamil Nadu and Andhra Pradesh. 15 lakhs patients visits. Around 50,000 patients visited this hospital for the HIV scale. Now, we started analyzing it. Soon after giving ART, there is a lot of people who were dying in this. Sudden drop, and then got stabilized like that. Then they thought something wrong in the analysis of it. Then they said yes, because they were dying because of the opportunistic infections or whatever, and so on and so forth. So whenever you have a sudden drop, you ask the question, are the patients leaving the study or are the patients dying much faster? Get two questions. So we would expect a slow, steady decline in the mortality. So how do we draw this? Okay. So this is, for example, I'm going to show you a data in this basis. Shall we do this small piece? What we are doing is a Kaplan-Meier survival estimate. Kaplan-Meier survival estimates. The first step in the analysis is that we have to estimate the probability of survival over time. Then the question comes, does it vary by gender, does it vary by comorbidities, risk factors? How do I answer this question? Shall we do this part? If you have your computer, just open SPSS. There is one data called John GT. This is from Jeyaseelan data from nephrology. So many years ago, I used to work closely with the nephrology. Okay. And so we did a lot of work. And this is one of his data is nephrology, something transplant data. So this is the question here is they were using that time the two immunosuppressants, prednisolone and cyclosporine. We wanted to see how the patients behave to two kinds of regimen. And so let us look at the data. We see there is a data called the John GT. Take time and open a folder, practical, whatever. Did you receive that mail? Okay, then open the Jeyaseelan Australia data. That is GTJAUS. There is one called the GTJ Jeyaseelan Australia. So when he was doing his something there, so he did this study. So I was this is Jeyaseelan GTJAUS. Okay. The question was, can you open the data that is SPSS?
I will do that.
Practical.
So this is the data set.
Yeah.
GT, G.
Do you have the data? GTJAS? Yeah. Can you see this data? Dialysis, yes or no, gender. There is one variable called peak antibody. The question which he had was if the peak antibodies were more than 20, whether he had a higher hazard for losing the graft. Losing the graft is the. So this is the question. So we said that the data details we have given you. If peak antibody levels are greater than 20, the hazard of losing the graft is very high. This is what is hypothesis. So therefore, we need to see what is the survival profile of these patients. How many patients do you have? How many had this disease? And how do I look at the profile? What is the profile and so on? Shall we do this one? We loaded, identify the data. Practically. GTJ, which is a space file, investigated. You are a space. Is that okay? Yeah.
In the example that you showed, for 2 days there was some sensor, but there was no movement. E-1. That is because even if you take the previous two, there the probability will be only 1.
Right.
So there's no issue.
For the question that you asked, the primary survival, you need to do odd ratio for the 3 categories based on status of each sector of the event. So right now for the question you asked, we don't need survival.
No. Ask me the question. If the question is that if someone had a peak antibody level more than 20, the hazard or odds of dying is much higher. No, the question is that the question is not, it's called the endpoint analysis. You are not interested in your time. So the survival analysis tells you that given a time point, who is dying, what are the hazards? So the time to event is considered as the survival analysis. The question which you asked is just you know the
So for now we are supposed to the event was
yeah. exercise given to you is just see in this data as a graph study. So what is happening? What is the median graph study? And what percentage of the subject had a graph failure? That kind of understanding, descriptive statistics. So how do you plot the curve and how do you summarize it? That is the question. If you are able to do that, then you wanted to see if someone had a less than 20 antibody, what was their profile? So that gives you more clarity than just doing endpoint. Is that okay? What do you understand? Okay. So okay. I just copy the bundle there. Now, see here, this is analyze. So you all know in spaces, analyze. The analysis part, you see survival. Can you see survival part module? The survival module, there is something called Kaplan, Meier and life table. Okay. Now, I'll explain what is life table method of plotting it. So, click Kaplan, Meier and it will ask you time and the status. So please remember always that time the survival analysis deals with the two outcomes. One is time and that event associated with the time. Okay. So therefore, you see here, this is dialysis. Where is my time? This is a transplant period. Is that the one? Okay. Put that one. And status is this. Status is 1. So let me look at it. How do I know that what is status? Just see the status. Censored and event occurred. 1 means event occurred. I am interested in 1. Okay. And the period is this. This is the time period at which the status has happened. This is a continuous video. Okay. Now I go back to analyze, survival. Take your time. Kaplan, Meier. This is transplant period, status, define event. Click here and say 1. Okay. Save what? Save survival probabilities. That is enough. And the plot, just see option. See here, these are options. The plot, just click I wanted survival. Okay. So let us look at this data. At time 0.08, that event occurred. The one event has occurred. And the estimate is this. The probability is survival is 99.5%. Okay. 0.130. I don't know exactly the timings. And this is the probability. And this goes on like that. This is the survey. How many subjects we had? So how many subjects we have? We started off with total number 216 subjects. 45 events had, 45 graft loss. And this is otherwise censored or they are with us, no graft loss. And this is the probability of survival. Curve, survival curve. Now, here we see median survival curve. Time is a very skewed data. Therefore, we deal with the median time interval, not mean time. Okay? Skewed observation. People are tend to live for longer time. Therefore, we don't present it with the mean statistics. But the data doesn't have mean time, median time, what do we present? What does it mean? Median probability. As I told you about the ART, the probability of surviving is 95%. So everybody survives for a longer time, 95%. Therefore, it doesn't touch the 50% probability. Do you understand? What is 50% probability? Median survival is what? 50% of the subjects survived up to what time? That is median survival. So what I have to do is 50% of the subject, probability of survival is 50%. I go here, I draw a line, 50%. It doesn't touch the curve at all. That means the survival probability is much higher than 50%. You understand? You can't ask the question, tell me what does 50% of the subjects survived up to what time? It has to come and cut the survival. 6 months or 12 months and so on. But that is not happening here today. If everybody survives up to 90%, 95%, where is the opportunity that 50% doesn't survive at all? You understand? So there was an examiner from LMC came to the rheumatology department. That lady is good. She knows about survival problem. What she did not know that the 50% median survival in some cases will not exist like this. Don't go with the concept that there's a 90%, there's no opportunity for you. We did the analysis, so statistics, not median, because there's no median there in that curve. Then Professor Ganda called me on the line and said, don't try to teach her. Tell her she's right. Otherwise, we explained the PG that in your case, there's no median because it's in mean. So he was able to explain to her, but she was not convinced. She told him, in survival analysis, you should give median. You cannot give mean statistics. And that told us, don't argue with the says he's like giving the. Please remember, this can happen in many places. When you say survival analysis, don't go with the concept that you will get only median. Okay. Imagine if the survival curve stays here, that 50% will not touch the survival. You cannot give. In that situation, you have to give mean survival. The results given here and the confidence interval. Okay. Now, this is the survival profile. Now you ask the question, what is the graft failure, end of 1 year or end of 6 months? You draw a line here and then go, say 80%. How do I get the data? You go to the table. What is your question? It gives you the cumulative probability of survival. Cumulative probability of survival. And this is the time. My interest, what proportion of patients survived or did not have a graft survival at the end of 6 months. So I go here and say 6 months is here and I draw this curve. So this is not there. I take 76.9. That's the probability of survival. Not losing the graft is 76% or 77%. You understand? Go to the time and draw this line and say, because your question is what proportion, we always surgeons will ask the question, what proportion of patients will die, will survive end of 5 years? So go to the time and draw a line and see the probability. So if you ask what percent is 75% of the patients survive up to what time, go to the probability, draw this line and get the time. Is that right? This is what summarizing it. Now, what is next? The curiosity comes. So this is what the summary statistics. If there is a median, you get the median statistics here. Okay, this is, so your survival curve come down like this and it will cut the 50% probability here. Now, this is any questions? So it gives you the details. Imagine, I told you, whenever there is a censoring, there is a list. Whenever there is a failure, there is a line. If I have 20,000 leprosy patients, do you think that I can handle 20,000 line listing of the patients' data? You understand my question? It is supposed to give 20,000 lines of analysis. So you can't deal with Kaplan-Meier survival analysis. The Kaplan-Meier survival analysis is meant for small students. Okay? And imagine that I told you about the 15 lakhs visits of the patients in Tambaram hospital. So you can't do a Kaplan-Meier survival analysis. What you need to do is you group the survivals into 0 to 6 months or 0 to 12 months. Then you deal with 8 to 10 such class intervals. Pull the data and do life table analysis. What do you do instead of each time point? You say group the time points into 0 to 6 months or enough number of patients. How many died? How many had relapsed? 6 to 12 months. 12 months to 18 months. So you cluster the patients into groups and do the survival analysis. It jumps from 0 to 6, 6 to 12, like that it comes. That is a step function and life table. So for various reasons, when you deal with thousands of cases, you do life table analysis to present your survival curve. But you need to say you have done life table analysis, not Kaplan-Meier. You understand this? This is very important. So that is why we use life table. Now, hospital setting, you deal with less number of patients. Therefore, you don't worry about it. You do Kaplan-Meier. As I said, the next question is the hypothesis points. He had a question whether If someone had peak antibody levels more than 20, whether his risk of hazard of losing the graft is more. We are not coming to the hazard question. We wanted to see, look at the profile of the patients. Okay. So what I'll do is, I'll go back to this. In SPSS, you see this icon. Can you see this icon? Click that icon. That will give you the history of analysis you have done. Click that Kaplan Meier, in which a factor is my peak antibody level, grouped. Compare factor. You all had about log rank test. Okay, we'll discuss about it. And so what does it do? It gives you the first statistics. Peak antibody levels less than or equal to 20. There are 148 patients, 21 had an event, and more than 21 to 80 or whatever, 17. And this is the rate, etc. So it gives you the survival probabilities. Okay. Now let us look at here. This is for 21 to 80, the next datum. Okay. And this is for the third group. If you want, you can regroup into two groups and do the analysis. So again, you don't have a median part here. A median cannot exist. So this is the mean. If you look at the mean estimate, say for example, mean survival time is much, the graph losing the survival time is higher. So let us look at this one. So 30. Longer, shorter, and shorter. See. So you have three groups. The profile is given to you. Now the first group stays longer. Those who had less than 20 antibody levels, their losing graph is much longer. Takes a lot of time to lose. Other groups are losing it much faster. Now the question is that whether it is significant or not. Whether it is significant or not. How do you know that whether it is significant? What do we mean by significant? When you say significant, it is not the difference of one particular time point. It is the whole profile being looked at. The whole profile is being looked at, the area. And to me, that these two curves are nearly similar, not much of a difference, but these two are different from this curve. So is it statistically significant? That is addressed by log rank test. There are three tests available: Meier, log rank, and threshold test. So we use in our department the Meier test. There is concept behind each test. The one test gives higher weightage for the earlier events. Meier is the one which is very conservative. There is a paper to say that why this is the case. So, but log rank test is very well popularly known in the medical community. And if we say write a paper, we did Meier test, and the examiner or a reviewer may not know what is Meier test. We write log rank test is happy. So you are also happy. No comments about this. So this is something. So this is the data. So now, are you okay with this? We are not interested. The sir asked the question: time to event analysis or event endpoint analysis? Something called the endpoint analysis. There was a question: early neonatal mortality. Early neonatal mortality, the child baby dies within a week. Okay? So someone did extensive analysis to find out within a week what are the risk factors for a baby to die. It was taken to pediatrician and even to her. She looked at the data and said, she said, the baby dies of day 3 or day 4. So I just look at early neonatal mortality as well. And this, when a time to event is very important, then you should go for this kind of survey. You understand my question? Whether the baby dies at day 1 or day 5, it doesn't make any sense. Very short period. You do endpoint. So therefore, when you wanted to do endpoint analysis, you should ask about when you have the time to your data, and if you want to do endpoint analysis, which is more informative. So if you want to do endpoint analysis, you don't need the follow-up time. Usually, people do not have that kind of data. Usually, cross-sectional studies. When you have a cohort studies and you have a time to even data, you should do this kind of analysis, which is much more. Yes.
Because same thing you get about notification also. People have my only who take the notification to.
That is what I'm trying. I was just saying now. If the time is very short period, it is whether you go time to event analysis or endpoint analysis is a lot of study. Doesn't make any sense. But infant mortality, if you take certain example, if that baby dies at 6 months, at 7 months, or 8 months, that is very important. Then I need to look at the time, median time of dying, and so on. So, when we are, we say the time is important, we have to do this thoroughly. I don't know why, what perspective they asked you to do this.
Kidney failure is into particular disease.
But do you have time?
So usually we did logistic regression that we are trying to predict.
That is right. When you have a time, you should do the time to, especially if you are there to area and uniformity. The time is very important.
We see this survival curves, they are all going uniformly from high to low. But if we see hazards, there are times that it can be high and it can come down and it can go low. For example, if you say normal life, early neonatal deaths, undersigned mortality will be, when you make it to 5, you may live into adolescence in adulthood. So, how do we reconcile?
Yeah, I showed you the different curves for hazard. The hazard varies from time to time. So sometimes it is high. The surgeons are soon after the surgery, the risk is hazard is very high and gets stabilized, and maybe after some time it increases. So therefore, it is not coming down uniformly or going up uniformly, and all the hazard will have different patterns. We'll come to that.
Madam, that MMC madam, the reason why she may have thought is that because the events are skewed, the time to events are usually skewed. Therefore, maybe the median period was in her mind.
No. Many people don't know there is something called a mean incident. They all go with the concept median survival. And median survival will not exist. The ART is a good example. The patient is on the ART, survival is 90%. There is opportunity for him to touch 50%. You understand? So in the cohort, everybody survives up to 90 and above. Well, you can't ask the question, what is the probability of survival up to 50%? So that doesn't happen. The wrong concept, misunderstand. They would not have explained it very clearly like this in this example. So in the absence of median, we give mean statistics, give a confidence interval. So that's something. Now this is, you ask the question, instead of say for example, go back here. in the options you can ask for the hazard. Remove that survey. So that will give you the hazard rate over time. So if you wanted to see how the hazard is moving, so it's increasing or and so on. So just see what happens. See, it is, as we started out with this survival coming down like this, the hazard is increasing like that. Over time, the hazard is increasing. Okay. This is the hazard is this. Do you see here? This is. But we don't deal with the basic analysis, deals with the survival part. The hazard comes in the multivariate concept. We don't look at pictorially the hazard part of it. But if you want, you can look at it. This is the reverse side of the survival. Any questions? Okay. Now, the afternoon session is going to be using art because the species doesn't additionally. What are we going to the species? The species doesn't have this some distribution. Sorry, hazard concept. Completely. So now, therefore, we wanted to sensitize you how to use R code slowly. Shall we do this? It's very easy. You are not going to remember any of the commands. But when you use R, what we are going to do is you have to have a set of commands, cut and paste and see what kind of work. Is that okay? Now we have given you, there is a PDF file, R code PDF. Can you please open it? I'll show you the PDF. So you have this PDF R code for survival and competing risk analysis. We have sent you this. Can you see this PDF? You have, just open it. The first part is simple survival analysis codes. This is the content. Okay. Can you see the codes? Can you see this one, this document? What I need to do is copy this part and paste it in the R window and run it. So we are going to train you how to do it. Is it okay? Are you ready? Now, we'll see. We'll spend some time because it is, you are not going to remember, but you know, these guys are cutting and pasting it and running it. That is all you need to know. Now, let me explain to you about the R software. The R software, if I am a scientist working on some area, I develop my codes. It allows me to put that codes as a package into the platform. That gives me credibility. Because I develop documents and work in use it. It's like almost doing the research and so all scientists contributed this kind of packages. And it allows other people to use it. So when you say package, there is a documentation. The documentation will give all the details. So that is what we are using. So therefore, I need to know which package will solve my problem. Google and find out. Say for example, the class is international university, very famous. He sent a paper for evaluation. They asked him to compare ROC curves. We all heard about ROC curves. Comparing ROC curves never happened. So he asked me, can you please tell the editor to I don't know how to do it. I remember many years ago I went to the station. So I did manually comparing ROC. So but we sit and work with this for us. So make sure we repeat it again. Google and find out whether the package installed. That is what we are going to do. We have done all this. So now we are going to do survival analysis. What is the package which will do this? Google and package for survival analysis. There are many packages. These are one package. Now, when it says, say for example, so but your file is in SPSS. So there must be a package which helps you to read the SPSS file into what the like foreign. The foreign is the package. Foreign is the package which allows you to read SPSS files. Therefore, I have to have it. Otherwise, I cannot read the SPSS. This is a survival analysis package. So this is another package which is necessary. Okay. So what I do is that I open R platform and copy these codes. See, you don't get that number sign, ampersand, but I just copy this and put it. I am going to open my, just watch me doing because I don't remember any of these things, but I have the documentation. So what I'll do is I'll go to R. This is my R. Okay. Click R. It opens a window. Then I'm saying, just see, wait here. It says this version is 4.2.3 and so on and so forth. Okay. This is, I just opened our platform. Now I see here, I'm saying I'm going to organize all my codes into a platform. So it's another window. Okay. Just organize it in the window and then I should be able to run it easily. So here, new script. So new script is an open blank window and this is tile vertically. So put one by one. Okay. What I do is I'll copy that. Just go here. I showed you the PDF file. Copy this. Do I remember a typo? I don't. What's are available? I just copy. What does it say? I read as if necessary, if require, you install that. Because I do this work every day, I would have installed the foreign already. So in my machine, it will ask me if needed, you install. For your machine, needed. Because first time you will do. You will install. It's called installing the package. Once. So what I do is I'll just copy this, do one by one, and click here. That is all. It is already there, it will not take time, but for you it will take a while. Okay, you can block the whole thing and do it. Can you please do it? Open your PDF file. Open your R. Shall I repeat it again?
That this is require internet to download it from the internet.
No,
Is there in the map R itself?
I told you there are some occasions. Now I repeat it again. Open, click R icon. This R icon. So open R icon. You get a. I clicked R icon. Okay. It gets loaded. And click a new script. Click a new script. Click new script. Okay. It will give you a blank window. Okay, blank window, and you just say organize it vertically, one by one. So that is all it is. So then what I do is this window, I copy my codes which are available from other sources. Okay, so I have my PDF. I copy this, copy. You see here, are you able to do that? And block the whole thing. So in which there are, you see the whatever it is in the code, foreign, survival, and surf minor. So 3 packages are getting loaded. So I can do survival analysis. Once you block this, you see here, this is the arrow key here. If you click that one, it runs. The output comes in this window. Okay. That means all these packages were loaded, ready for. Then what you need to do is, the package is loaded, activate the library. No, this is a library of these softwares. For an example, it's like this. You copy this one also, ggplot is, okay, to do the plotting. So put that one also here and run it. Okay. What is next? I go to my code. Packages are loaded. Then you ask for the library to get loaded. Copy this. Copy the libraries, activate the libraries, block and run it, block and run. So you can create SPSS file, you can do survival analysis anytime. So some people have to have a package to be installed. So we have to keep that. Yes. Yeah, hazardous. Basically, hazardous not problem. Probability takes the value 0 to 1. Hazardous probability of happening an event. Very short. Let's say interval. Interval is various. It is 1 week is probably 1 month. It varies. So the probability of happening an event at a particular time divided per year or per month. Because you change the time, it is not probable. Probability is divided by it. So it becomes more than 1. Hazard. Hazard rate. Let's say the rate of life is 5 for each law. For large is 2. Now it's just 2 hazards. Take the ratio of that there's one you have raised an important question. When you see a curve, there is a line coming up. So it means there's a failure occurred at that particular point in time. But the whole survival analysis assumes a very important concept that is called censoring occurs uniformly over the period of time. Please remember. Because sometimes the trials people don't like your treatment, new treatment, therefore they are leaving much faster. So dropout happens much faster. I told you that HIV example, people died of opportunistic infections as soon as you start with them on HIV. Yeah. So there is a drop. Now you wanted to know, is it really because they are dying or there is a censoring? Is it happening evenly over a period of time? What does it mean? That, say for example, here, this is a very important assumption which we have. This is time. What we wanted is that censoring happens over a period of time like this. This is what we expect. When you plot the censoring data, this is what should happen. Supposing that this graph, this is the new treatment. This is not evenly happening. So this you have to plot and see. This happens that you need to understand why this is happening. So when you review a paper, good papers, journals will ask you this. So when you do Kaplan Meier, I will show you some colors. They also wanted to know. People claim that I have done a 10-year follow-up study. They'll ask you how many subjects you had in that 9th, 10th. I have only 10 subjects. So you start out with 1,000 subjects. How many are available in end of 8th year or 9th year? You have to give that detail as this time. This is 1, 2, 3, 4, 5, 6, 7. You have to say I started out with 1,000 subjects. How many are available here? 100? 200? This data we need to provide under the Kaplan Meier survey. The spaces doesn't do, but the R will do. This is very informative. You can claim I have done 10 years, 15 years, for how many subjects are available. That you need to ask the question. This is very important. So, is it okay? Now say for example, madam wanted, how can I compare only 2 graphs? Only 2 survival curves, not 3. Go to SPSS. The easiest way of doing it, the status, you have a status column here. Okay. This says censored and so on. But you are grouping, there are 3 groups you deal with. This is, say for an example, this is a peak antibody level, has got 3 groups. I don't want to have that over 80 because small number of observations are there. The simplest way is just say the 3 is the missing value. It doesn't get analyzed at all. How do I do it? How do I do it? Peak antibody level, there is a missing value here. Then you say 3. Do you see? So it is going to deal with 1 and 2 group. So then if you do the analysis, so you deal with only 2 groups and the p-value is meant for only 2 groups. The hazard of dying is much higher for this group, green color, and 21 to 80, and it is highly significant. Okay, instead of selecting the data and so on. This is the easiest way of doing it. Is that okay? So we'll have a small tea break and come back and see. You'd appreciate that R code, how it is very useful.
EPIDEMIOLOGY. Check.
Shall we start? So, what we have done so far is just the step one analysis of how do you look at the profile of the survival and compare two or more survival curves. It's a log rank test. Now, I'm not going to, time permits, I'd say the logic behind this log rank test and all that it is necessary now at the moment. Anyway, we'll see some of the points have to be noted down. So we are into R code. I wanted you to copy and run the R code and use the same data or any data and see whether you are able to produce the Kaplan Meier curve. Okay. The R graphs are very powerful and you can play with the colors, etc., thick line, and so on and so forth. And this is what I said, Dr. Jeyaseelan data, and from nephrology. This is, but you have to send that Excel file. Yeah. That particular AUJ is there. Australia that we have seen. This is another data. Okay. Ovarian. This is ovarian. Okay. So we'll go to that one. So this is when you have a specific data, you can read it. And yeah. Now let us. I'll explain to open your PDF file. You have your PDF file? Yeah. This is your PDF file. Many times the packages come with the sample data. When I write a package, I have to provide you a data set to work with. In that package, there is a data called the ovarian cancer data. Okay. So I don't have to write a read statement, take it from SPSS or Excel, because when I put the data in the package, it is already available. If you mention the data name, that gets loaded. Okay. One such data is called the ovarian data here in this package. Okay. This is, can you see this one? This is ovarian data. Now, you have loaded these packages, this one, and type ovarian and see what happens. Once you loaded your library and data ovarian, or okay, just say data of Oh, no. Okay. Wait. Oh, they will practice now. So when you type just ovarian, and it gives you the follow-up time, follow-up status, age, residential status, treatment, and the ECOG value code. These are all the covariates. The time and status are important. Can you see this one? Now what we are going to do is that we are going to see how we are going to do the Kaplan-Meier survival analysis here. But I don't remember the code. I don't know where to go. Go to the PDF file. See here, KM. See here, the KM is something which I give. Does not mean KM survival. You can say whatever your name, L.Jeyaseelan, something like that. It doesn't matter. It gets, the whole information gets stored into the name called KM. I can change it to any name. Okay. Doesn't mean that you have to give the same name here. Please remember this. What does it mean? The whole information comes out of this. This process is stored into KM. And when you say summary of KM, it gives you everything. So when I do this one, see that what we got in SPSS comes out of this, like your number of events, survival probability, standard error, confidence interval, etc. So this is, therefore what I do is I just copy this one. If my, copy this one, what is the data name? Ovarian data. Okay. Copy this. I don't remember anything, just copy this. Okay. I don't want this KM, or you can say, I say LJ. Because this is what it is. But this you cannot change this one. Because the data is ovarian data. This is very important, which has variable called follow-up time, follow-up status. You see here, these are, you should not change this. So when you do this one and Control R, the first one, and summary of LJ, not KM. I'm just telling you that you can do anything, you can give any name you want. This is what you get. Okay, summary is given to you. The summary is not like what we have got in SPSS. Now, so what is next? Go to the PDF. This is what the summary you got. This is what important. Print this one. Copy this one. Print the results. I need to change this as LJ. Print. So the total number is 26 ovarian cancer patients. 12 events have happened. The mean is this, and standard error is this. The median time is 638, and the confidence interval is given to you. So the upper limit of the confidence interval is not able to be defined. Let's see the curve. This is to get the summary print. Okay. And I need to go to the PDF. Did I ask for this? Plot KM curve. Any clue? What should I do? LJ. Not KM, LJ. Ah. Then it should not be there. This is just the title. You have to copy this GG plot. Just remove that one. Just put this thing. When you put the ampersand, it becomes comment. It will not run. It's not an executable. So this is LJ. Data ovarian, and you don't worry about anything. So this is, what is this for? Same curve you get. Okay. And this is the follow-up time. This part you don't get in SPS. Each time point that how many subjects are observed. So you have said that, say for example, 1,200 and 1,200 days follow-up, you had only 2 subjects here and 4 subjects here. And this is the curve. Number of subjects available at that point in time, excluding censor and death. No, it is, say for example here, when they come down, either there is a death here. Whenever there is a coming down part, there is a death and as well as a change in the censor. Do you understand this? Okay. So when there is, say for example, let us go to the data. Ovarian. This is your data. Edit of your file name will display the data to you. Okay. This is the data. Follow-up time. This is not sorted in order. We need to sort and find out. And if you take 120, do you see 120 or something? You don't see nothing has happened. 115, there is a death here. And it may not be exactly 120, it may be 115 or something like that. Okay. So let us look at this data. This is in order. At 156, there was 1 death. So far, there are 3 deaths happened so far up to 156 days. 120 days, up to 120 days, there are 2 deaths. So as and when there is a death, there will be a drop in your probability. Okay. As I said that it is this curve, when you look at this curve, looks like very much a step function, life table curve. Do you remember I said put the time into every 1 month or 2 months, count the number of deaths, and comes like this. As compared to the earlier curves, as and when there is a death, it will drop line like this. Okay, so this is called a step function. So the time is 120 to 240 or whatever, group together and put the death, or there's no death happening in between, and so on. So, any question? Yes. Plus is sensor. That particular point in time, there was a sensory. Plus indicates a sensory. Dead. The plus indicates there's a sensory. Is it okay? So you could see that at particular point in time there are more pluses, then it means that a lot of censoring happening there. Let us look at the PDF file. The PDF file, the first command gives you just a simple concept of this, and I wanted to see that by ECOG status, okay, score. So what happens? How does the survival behave when I put a covariate into the analysis? Then you see here, there are two groups here, and the one is doing much better, other one is after some time coming down. There's not much of a difference between the two, and it comes down here. It's a small data. So this is what you would see. Now, how do I do it? Copy this. This is the one. Compare Kaplan-Meier survival curve by ECOG performance using log rank test. Okay. Copy this and paste it in your R and run it. See what? Can you do this? Copy this. Now, do you see any covariates here? Shall I put this instead of ECOG status? Can I do the analysis by treatment? How do I do it? The code given is meant for ECOG. I wanted to change this. Instead of ECOG, I wanted to put a covariate called a treatment RX. Just delete that ECOG and put RX. Okay. So this is, I'll just remove this ECOG. And there is a variable called RX. You see the treatment? So I'll put RX here and block and run it. So I'll also change this ECOG. Instead of ECOG, I'll put this as RX. Summary of this KMRX. Is that right? So data is same, ovarian data. Instead of ECOG, I wanted to put this variable treatment for the analysis and summarize. Gives you this treatment equal to 1, the survival profile, and treatment equal to 2, survival profile, So you are ready? And if you wanted to put a GG plot for that, do we have, can you please check your code? GG plot code, copy this, copy here. It's not ECOG, this is RX. You see RX is here, okay? I have not changed anything. Looks like I don't have to change. Do you have this graph? This is by treatment. Treatment 1 and 2. Whether the profile is different or not. Is it difficult, madam? Can you do this? Instead of seeing ECOG, I'm just changing it to treatment, RX. I'm changing only the variable name. Do you understand this? The code which is given in the PDF file is for ECOG. I don't want the ECOG. I wanted to look at the treatment, by treatment, the survival curve. So instead of ECOG, I changed treatment. So let me explain again. So let me explain this. Can you please look at this one? Look at this. This is, I'm saying, naming it like earlier I said LJ, I can put LJRX or you can put your name. But the steady variable now I am having is RX, treatment. So fit the survival analysis, survival curve using these two variables. That is a very important entity in the analysis, ovarian data, follow-up time and status. That will not change. You are saying that model it for, analyze it by treatment, 1 or 2. Data is ovarian, that is all. Okay. And provide the summary of this. The whole information, this detail goes into the name called KMRX. You can give anything you want. I can change it as treatment though. R is case sensitive. Use capital letters, you have to use capital letters. Okay? Because I have used this RX in my data, I just use the same thing. So just run this and provide me the summary. That is what we are saying. Gives you this. So this is treatment 1 and treatment 2. Then what I'm saying is the whole information, all data, the produced output information went into this name called the KMRX. Use this for the plot. You should not change it. Use it for the plot. And I don't do anything else, just block this and run. So when you run it, the cloud or the plots, first time only will show you the plot. Next time you have to go to the window and say graphics, this one device gives you this. How do I copy it? That save as copy as a bitmap. Is that right? Bitmap? Oh, yeah. So, and then you just go to your R, Word. Usually, when you make a manuscript graph, you don't put the p-value here, labeling in the graph, labeling on the top, but that is not accepted. So what you have to do is you should not put the p-value here, and the legend has to come at the end or outside the graph, or at the maximum at the bottom of the graph. You can do it. Okay, and then I would not even put this box and all that. Only x-axis line and y-axis line. Not have this. That upset the look of the graph. Okay, and see this. This is a, if there is a line. I don't know what is this line. We'll have to say the 50th percentile. The median survival time is around 600 plus. Don't put this line and all that. Just you have to have two lines. There is a censoring here and there. So that is all it tells you. And how do I do it? So what you can do is, if there is in the graph code, you can work with the statistician or Madan to remove. Do you see p value somewhere here in the code? P value 2, yeah. Just say false. So median line, if we put this ampersand, it does not run. It becomes a comment. So let us look at this one. What happens? Just do it again. You don't see the p-value here. Okay, p-value should come in the text. And you don't see the line here. The core codes are available. Core codes are available. You can do little, you can change your colors, etc. Some people don't like this is a yellow color or whatever. You can change it. Okay, that is a minor thing. So the p-value is a log rank test p-value. What does it tell you? The whole profile, the distance which you see, is it statistically significant? Or that the distance which you see is a random? Okay, looks like very impressive. Is it statistically significant? So this is basically a chi-square test. Any question? Okay, I went back to my slides now. Any questions? So, do you have any questions? No. Supposing they ask you to give the editorial board ask you to give the confidence interval for the curve. That you see, you can give that code here. So this kind of thing. So plot and this is, I think this this is I think that part is missing. I'll just check with him. I'll come back to this. What is the code which gives you this? Yeah, this is the one. I'll just copy this one. What you need is a code. Go back here. So what should I put? Plot equal to KMRX. Anyway, I'll come back to this command plot. Confidence interval. We'll revisit this one. This is basically at each time point there is a failure. It calculates what is the expected death, what is observed death, and that's the chi-square test. It's a simple chi-square test as and when there is a failure. So each time point there is a failure, it does the chi-square test and sum them up. So that is called a log rank test. So let us not worry that the codes are given to you to do this test. And this is what we have said. And this graph, this should not come here. This legend should come at the bottom. It should not obstruct your graph lines and so on. Please remember this is very important. And this gives you the p-value, whether it is significant or not. And now, are you okay with the Kaplan Meier? Are you comfortable? You can use R code to do this one. Yes. Kaplan Meier, there is the SPSS gives a typical Kaplan Meier. As and when there is a failure, it gives you log. Yeah. Yeah. It is yes. Yeah. They wanted to know what is the denominator. That is all they wanted to know. Not much detail. At that end of 1 year, how many subjects are available with you? End of 2 year, how many subjects are available with you? That is all they wanted to know. Denominator. Numerator, yeah, you don't get that number. No, only the numerator. That too. Censored. Yeah, that is a say an example. This is which graph is this? Now let us look at the R output. Let us look at the PDF. This is, if we look at this, what R gives. Yeah, Barney, this is what you get from the R. This is 26 subjects available totally. After 300 days, 12 and 10. The numbers are available, and this is 1 and 1. This is a detail you wanted to see. So if you wanted to take information from your data, I would like to see that, because a good number of observations are available up to this time point. After that, I am not interested as a reader, because it gives me clarity on how many subjects are being followed. That information has to be given to readers. You don't have to give it to specifics. You can say at least total number of observations. Yeah, yeah. Yeah, yeah. That you have to manually do it if you wanted to give clarity to it, that whether the people are leaving the study or dying for some other causes and things like that. So either death or dropout and the total. So that will give you clarity, but unfortunately that is not given in detail. Now, Are we ready to move on to Cox proportional hazard model? Now, so far we looked at one variable at a time, like immunosuppression, yes or no, or two immunosuppressants, and so on. So gender, ECOG, treatment, so the survival curves were given to you. That is the first step of any survival analysis. Okay. And the next one is Cox multivariate concept. Cox proportional hazard. Cox is the name of a scientist who came out with this method in 1970s. Okay. Yeah. Yeah. Yes. That is what we. Oh yes. So something you need to decide what define what is your outcome of interest. Yeah. It's like a composite outcome you can do. Yeah. Now he's saying when for various good reasons numbers are small in a particular outcome, you make a composite outcome. So just define what is your outcome and do the analysis. Now, first I wanted to tell you about Cox proportional hazard model. Before I go there, I just wanted to refresh on regression concept to you. This is the regression concept. This is a linear regression equation. This is a linear regression. The systolic blood pressure is a function of constant term and the age. So the concept is as the age increases, what is the corresponding change in the systolic blood pressure? How do you do it? The slope 0.97 is a slope B1 or beta 1. Okay, B1. This is what y equal to a mx plus c, which we all studied in schools. This is slope 0.97. It says 1 year increase in your age, corresponding change in your systolic blood pressure. So if there is a 1 year change, there is a 1 unit increase in your systolic blood pressure, corresponding change. Now in survival analysis, we are going to see in terms of hazard, how many times the hazard changes in terms of ratio, and so on. So this is here. So therefore, if we see that the change is that when there is no change, x equal to 0. When there is a 1 year change, x plus 1, the difference is this. Basically, when I say 1 unit change as against no change, so this is please understand this comparison. No change, this is the slope, that only constant term. When there is a 1 year change, it increases like this. So it basically means no change versus 1 year change. The difference is 1 year, you multiply it with the slope. This is what we are going to do. In the categorical data analysis, logistic regression analysis, or survival analysis, what we do is, we don't ask the question of how many 1 year change and all. Many times that if someone is a smoker, someone is a diabetes, someone is something, so therefore, how many times the risk increase, hazard increases? Don't use the word risk, hazard increases. That is a concept which we have here. So now, the important point what we need to remember is this. When you have a variable like packs of cigarettes, your pack you're smoking, birth weight in grams, and calorie intake is in 2,400, 500, 3,500. So therefore, when you say what is 1 unit change in your calorie, so 1 unit change is a very tiny change in your regular. There we said 1 year age changes, it's a big change. only a calorie or only a gram in change, the corresponding slope has to be very negligible. Do you understand? Now, what happens invariably? This is what we get. So 1 gram change, the corresponding change in the slope is this much. My eyes tells me what is the regression coefficient is almost 0. Why should I worry about it? But when I say this is 500 gram change, mother is able to gain 100 grams or 200 grams. When you multiply this with 100 or 200 or 500, it's a big change. So the message what you need to have is that if you see data like this in the regression coefficient, don't assume that this is useless, insignificant. So you need to ask the question, what is the unit of measurement? And that for that variable. If it is very tiny in terms of grams, in kind of calorie, it's a very important change. So when you do this calculation, there is a big effect. So 1000 grams change in the birth weight. There's a 50% reduction in the mortality rate. So this is a very important change. Next one is about how to use dummy variables. Many times R takes care of dummy variables by itself or any other SPSS software that you use. It creates what is dummy variable first or indicator variable. I have 3 age categories: less than 49 years, 50 to 59 years, and 60 plus years. So the SPSS or any standard softwares will give you a matrix before it goes to any further analysis. You should be able to read and document that matrix. It tells you in your data, you see here 0 and 0. When there are 3 categories, there will be 2 dummy variables. What does it mean? When you have 3 categories, it tells you you have to keep one category as a comparator category. Therefore, you compare the next 2 categories with the other categories. You asked me the question, when you have 3 groups, how do I compare? So this is, so it keeps one category as the comparator and compares the next category with the comparator, next one with the comparator, and so on. What is a comparator? Next month I would not know. So there must be a documentation what was kept as a comparator. The comparator is this. The moment you see SPSS output or any output, this, the 2 dummy variables, age was made as 2 dummy variables, in which one dummy variable was the 2 dummy variables had 0 and 0, which means this is the comparator category. Less than or equal to 49 is the comparator. Always SPSS takes the lowest category as a comparator. If you have to change it, you'll have to change it. Now this is an example. What does it mean here? 50 to 59 is indicated here. And it goes with this, the first dummy variable. So 50 to 59 years is age R1. 60 to 60 plus is indicated in the age R2. So age R2 means 60 plus as compared to 49, and 50 to 59 is age R1 compared to 40. So you should be able to read and understand this. It doesn't give you age 50 to 59, age 60 plus and all that. It will give you age 1, age 2. That is all it will give you. But you need to find out what is age 1, what is age 2 from the documentation. So remember, today perspective is about a variable. This is competing event. I remember nephrology, those days we used to have transplant programs where infections were very high, hepatitis B and TB and so on. that they were killing the patients. At that time when we do the analysis that we did, we put someone had a hepatitis B taken out of the study since then. So today you call it as a competing event. They can also kill the patients as broadly infections. I remember Jasti used to tell us we were able to brought down that infections from 15% to 6% or 7% today in our hospital is a big achievement, and so on and so forth. If we say infections also trying to kill the patients, various reasons about graft failure or whatever, they are also dying due to that one. That is your interest. So today we are talking about competing events. When I have a myocardial infarction, patient died of stroke. How do we handle this? What has been going on in the last 20 years is that you adjust for it. Adjust for the stroke. Adjust for the stroke means they are saying censor it. Okay, or put that stroke information in the regression analysis, it gets adjusted. Stroke effect is taken away. So these are all wrong analysis. So therefore, today when you talk about survival analysis, when you say adjust for it, what does that really mean? I can adjust for age, I can adjust for gender. They will not cause someone to die. But if there is a covariate which is responsible, that is also trying to kill somebody, then it is, you should not be adjusting for it. You should do the competing event. So therefore, the adjusting is a very funny thing today. We need to be very careful in survival analysis perspective. So also that what we need to do is we have the habit of putting all the variables to adjust for it. This is a risk factor, adjust for it, adjust for it. When we should not adjust for it. That I just wanted to highlight. This is the data. This is in Indonesia. There was a study which was done in 1990s. This is the hospitals were given an extensive care, more care, and the traditionally provided care in the primary health centers for reducing neonatal mortality. These are all two settings, less care and more care. The overall relative risk is 2.73. So what does it tell you? It tells you that those who received less care are 3 times more likely to the baby is likely to die. This is what the overall analysis is. When you look at, I'm not trying to teach you what is confounding interaction, but you just remember this. When you split the data into 2 clinics which received, where you see here the mortality is 7 out of 476, that is the mortality rate is proportion is 1.68%, or very low as compared to 8% in this other group clinic. What does it tell you? That the setting itself deals with lower and higher mortality. So you pull together, you get the average of both, which is not correct. When you look at separately, that the risk of dying is different. So nearly same, the risk is same, 1.2, and here it is 1. Okay. This is typically called confounding. The relative risk is nearly same in both the group, you can adjust for it. Okay. When you adjust for it, what would be the right answer you would get? Here 1.2, here nearly 1. So it may be 1.1 or something like that. But the pooled data gave you 2.7 or 8 something, which is wrong result. Okay. So now this is, so therefore you need to look at the stratum specific analysis and see whether it is worth pooling it, adjusting for it, and so on. What I wanted to tell you is when you should not adjust. Survival analysis. We are going to do some exercise. This is one statum. This is not writing. Hazard rate equal to 2, hazard rate equal to 2.5. Then you can adjust for. If 2 and 2, that is 2.5. That's nearly same. So when do you call this as a effect confounder? If there's something called the crude. If the crude is, say, for an example, 4, crude is 4, pull the data together, your hazard rate is 4. But when you do stratum specific analysis, it is around 2. Then we are supposed to adjust and provide the data as a correct information as 2.2. Do you understand? The crude 4 is wrong. That 4 is because of a confounding effect. So you are supposed to tease this out by taking a separate statement and do the analysis. And the correct result is 2.2. Now this is what adjusting for confounding. When you do regression analysis, it does correctly the same kind of analysis. Now I'm going to give you another scenario where the HR is 2 here, hazard ratio. The HR is 8 here. What does it suggest? Should I adjust for it? Take the average? No, you should not. It tells you there is something going on between two variables in this stratum, that there is an interaction going on. Therefore, we need to present it as such. If you can do the modeling properly, we can say this is 8 times more, whereas in the other stratum, it is only 2 times more. So you should not do any adjustment. This is called effect modification or interaction. You should not do anything. So when you do Cox proportional hazard model, the same concept comes again. You need to see, how do I know that it is a confounding or effect modification? So, take an example. In your survival curve, it comes like this. Instead of hazard ratio, I would be ready to do the adjustment here because they are nearly same. But when you see here, there are 2 different profiles. So I should not do the adjustment and put one line in the middle, which is not correct. Suppressing that information. Adjusted should not be done. So you just keep watching for this kind of curves and decide whether you want to do stratum specific analysis. Don't put that variable in the model. So this is what we are going to discuss. Now, effect modifier is that you need to code it in such a way that you are able to bring that 8 as a hazard ratio. Regression analysis only. Oh yeah, regression analysis only. So this is the message is that when you have your own data and if you have the computing power, you should do a lot of subgroup analysis and try to bring out that kind of thing. If you give it to the statistician, they'll ask you the variables and put it in the model. 5 minutes, I'll give you the results. I'll suppress a lot of information. If you have the computing power, you should be able to take it out. You know the biology. So that is why it is important for you to learn how to do this. Now, let me introduce Cox. Yes. Yes. No, effect modification will tell you. Effect modification is interaction. Interaction will amplify or suppress that information. Yeah, both ways. It is an antagonism as well as a synergism. So it could be either way. So our job is to find out what is happening now. Okay. When are you ready? If you look at the Staten specific analysis, if the odds ratio relative is nearly same, you can take the average as against the crude. The crude is also same that you don't have to adjust for. The crude is 4 and these are all 2 and 2, then the 2 and 2 average is the right answer. Now, this is combination of explanatory variables affect the form of hazard function. Hazard is called Cox, Dr. Cox is a person who came out with this theory. 1970s, very popularly used statistical methods in the world. And he used hazard function. What is his theory? He said everybody has a baseline hazard to die. There's a baseline hazard for the disease, and it gets amplified when there is a risk factor. So therefore, say for example, he said this is baseline hazard. When you do some kind of algebra, what this? Hazard at a particular point in time, there is a baseline hazard. So how do we measure baseline hazard? So let's see what is baseline hazard E means. So this is the risk factor, X. Male or female, smokers or non-smokers, dialysis, yes or no. And these are all the covariates. Age of the patients and so on. So the ratio of the two hazard, that means the baseline hazard to hazard at any given point in time, end of 5 years or 3 years, is a function of the risk factor, E power this. We found the way to estimate this unknown variables like beta and so on. Okay. Now I'll come back to this again. What is important concept here? Why it is called the proportional hazard model? The hazard is the one he is dealing with the hazard, not survival S of t, but he is dealing with H of t hazard. His theory is a very important theory. He said, I told you, I have shown you the hazard graphs varying over a period of time. What he said was, if there are patients who had a dialysis and no dialysis, two group of patients. So what he said was, you take a dialysis patient, his hazard is much lower as compared to no dialysis patient, or vice versa. At any point in time, if you take the hazard ratio, it is going to be same. Do you understand this? You measure the hazard at 6 months, you measure the hazard as 24 months, the ratio is going to be 2, 2, 2, 2, 2 for an example. The hazard ratio does not change. It's called a proportionality assumption. So everybody accepted that assumption. And you need to check whether your data follows that assumption when you do this. Sometimes many variables will not follow that assumption. Okay? Now, this is what is proportional hazard model. So this is a very important assumption. And remember, the X variable does not involve T. What is time? It does not change over a period of time. I go to nephrology for transplant program. So they measure my baseline variable. After that, they will not measure anything else, for an example. Then it becomes time independent covariance. Age of the patient, age of the donor, diabetes status, family history, everything is measured at the baseline. But if they keep measuring their hemoglobin level during the follow-up or after the transplant program, transplant, then it keeps changing. Okay. Do you understand this is? So if the variables of proteinuria changing over a period of time and they wanted to model it as a risk factor, then it is a time dependent code. So how do you write that? You write say that, for example, proteinuria changes over a period of time, then you say proteinuria T. So your model can be a function of, say for example, X plus Y and T. These are all time dependent coefficients. Or Z. Why you don't wait, because it is meant for dependent variable. Z. So we are not going to say how do you deal with the time dependent covariates? Because many risk factors are very changing over a period of time. So we are dealing only with time independent covariates, static variables measured at the baseline. So therefore, if we take this, those who had dialysis and who did not have dialysis, the regression coefficient is 0.24. Take an anti-logarithm of it, e power 0.24, it becomes 1.28, 1.3. The hazard of losing the graft or losing the patient is 1.3 times more if he has had dialysis. When you have a continuous variable, that is, because what is the difference between 0 and 1? 1 unit. Do you understand? 0 and 1, the difference is 1 unit. So 1 unit change, what is the corresponding hazard? Suppose if we take age, this is, if someone moves from 55 to 65 years, the difference is 10 years. So 10 years multiplied by regression coefficient, and then you take e power of. Do you understand? So supposing if I say, if I age by 1 year, the hazard of dying is 1 times more. So if I age by 5 years, you should not say, please remember, you should not say 5 times 1.5 is the kind of risk. What you need to do is you have to multiply the regression coefficient with the 5 and then take an anti-logarithm of it and give the correct answer. Take the difference between x1 and x2, the dialysis and no dialysis, 0 and 1, the difference is 1. 55 years minus 65 years, the difference is 10 years. Multiply that with the regression coefficient, take an anti-logarithm of it. Okay? That is how we need to provide the risk. Now, this is what you'll have to do. This is the model which we have. Please remember, these variables have no assumption at all. It could be continuous, categorical, ordinal, and so on and so forth. So there is no assumption about independent variables. So you can have any number, any types of variables. So it gives you, that is, so they had two kinds of immunosuppressants. One is prednisolone and cyclosporine. If somebody had a prednisolone, the risk of hazard of losing the graft is 3 times more. That is the results and the confidence interval and so on. It is highly significant, etc. This is the Cox proportional hazard model. What all you have to do is you should specify your data, and these are all the covariates, immunosuppressant and age of the patient, and this is time and failure status, and copy and paste it and change your variables and run the model. Easy. Now, this is a concept which is used to see whether your data follows proportionality as well. It's a very important thing which you need to say. When you write a paper in methodology, you have to say, we use log minus log S of t curve to test whether the data followed proportionality as well. Because he assumed that at any point in time, the ratio of the two hazards are same. Either it is first year or 5th year, the ratio is same. Is it true? So that is done, validated by this graph. You are supposed to do this. Now, so this is a multivariable technique, and first we'll use this. Look at this graph. This is log minus log S of t for two regimens. Do you say that the immunosuppressant variable follows proportionality assumption? No. They are trying to cross each, almost touch to each other, and this. Whereas the other one, they also cross to each other, the liver disease. So I will not put this variable in the regression analysis, Cox proportional hazard model, because it violates the assumption. Or when you do a regression analysis, you have to ask for log minus log S of t and see whether you get a straight line. Straight line means it follows proportionality. So this is so small tips will give you some data and see, should I do regression analysis, Cox proportional model and then remove the analysis? You don't have to do that. Kaplan Meier itself you can do. Find out what is violating assumption. So this is, in this situation, we advise you to do a separately the analysis for two regimens and present the data. If anything violates assumption. Okay. Open your SPSS. So SPSS is easy to use. Then we'll come back to R. Now, if you go to your data, practical data, there is something called the Anderson data. Anderson data has a treatment. Can you see this one? You open your data. This is a leukemia study or something like a cancer related study. You have log WBC values and the treatment and gender. You have this variable, Anderson data. Is that okay? There is a time in weeks and status, censored and not censored. And quickly do the Kaplan-Meier survival analysis by gender. Analyze survival, Kaplan-Meier. So you have to put the time variable here, status here, define the event 1, and factor is gender. Compare factor, log rank, and options, survival. I don't want to save anything. Just see whether you have done it. Are you okay? So you have, we are doing Kaplan-Meier survival. So you have the time and the probabilities here. Okay. At the 5th month, 5th week, there is one death, and 6th week, there is a relapse, at the 2 relapse. This is a cumulative number of events, totally 2, and so on. This is for female, this is for male, this is for male. These are all the statistics, summary statistics. You have the median part. So therefore, your survival curve should be crossing the 50th percentile, 50th median values. Now let me see. Let me ask you this. Just wanted to ask you, this is, can I use gender as a variable in the regression model if I do Cox proportional hazard? No, because they are crossing each other. Potential variable to violate the Cox proportional hazard model essentially. If you take the inverse of it, the hazard will cross each other. They should not. So ideally, the Cox assumption of proportionality can be studied using the SFT curve, survival curve. So ideally, if there is a proportionality, if there is a proportionality, it should be like this. Parallel to each other. There is a shift. The shift has to be remained same over a period of time. Do you understand this? This can be picked up from the SFT analysis itself, survival curve analysis itself. If they violate, they will cross each other. Okay. Therefore, you should not put this variable in the analysis. Now, similarly, so you can study each variable like this. This is what I do, or we do in our department. Look at. Is that okay? Now let us go to the, yes. Yeah. No, we don't use the word risk here. It is only hazard. What is that? Only hazard. This is typically because typically risk means the probability. Say for example that this is there is a hazard. Say for example TB. When I am younger, the hazard of getting a TB is higher, and when I become adult, it is less. So sorry, for an example, this is lower when I am younger. When I become adult, I go out and get TB more, and it comes down like that. So this is for non-smokers. This is for TB. Disease is TB. When I am adult, I go outside, I contact the disease, come back, I get infected. Then say for example, this is my smokers. I'm taking smokers. Smokers have a higher risk. So the higher risk increases when they are adult. The higher risk decreases when they are small, and so on. This is called the ratio, hazard for hazard ratio, hazard for non-smokers, hazard for smokers. The ratio is, for example, 3. The 3 is expected to be similar everywhere. This is his assumption. You understand this? The hazard itself is varying over a period of time. It is high surgery, soon after the surgery, it is very high, comes down, and so on. Yeah. Okay. The time. No, it is not. I mean, basically, it is not defining thoroughly the hazard and all that. So what I'm saying is, hazard is the rate at which the TB is coming. Hazard is a rate. If there are 100 individuals exposed, the hazard of getting this thing is at this particular point in time is different. At this particular point in time is different. So on. Yeah, instantaneous. Yeah, hazard. Yes, for that it gets amplified, increased when someone is a smoker. So when you take a ratio of these two things, it remains constant over a period of time. That is what is. You don't agree to this. So therefore, that the analysis needs some kind of justification whether your data follows that kind of assumption or not. If it doesn't follow assumption, one variable violated that assumption, you do separately this analysis. That is the advice we have. There are many methods of doing it. We are just doing only this much. So I think I sent the paper. I don't know whether Madan sent the publications earlier. In which the second paper we wrote with Dr. Stephen Walter, McMaster University, to introduce Cox proposal as a model. Got published in National Medical Journal many years ago. So we were trying to teach this technique, and the various pictures we have explained what is hazard ratio, what is this model assumption, how do you test it and all. So the message what we have discussed so far is simple Kaplan-Meier curve will tell you that variable is going to violate the assumption or not. You don't have to complicate yourself. Simple Kaplan-Meier curves will tell you whether it is going to be followed, assumption is met or not. That is what we wanted to see. Now let us go and do the regression analysis. The Cox proportional hazard model. The data what we have given is that say for example you take Josh T. John Australia data, peak antibody level. The question of interest is peak antibody level. There are many covariates. So many covariates because he has got many covariates because he has to write a thesis to add this. So I just analyzed the data and sent it by email and so on. So this is now I remember he said if someone had the rejection episode, more number of rejection episode, peak antibody level, and there's one more variable he was interested in. So I don't remember that. What is his interest? If someone had more than the antibody level more than 20, whether the hazard is more or not. Is it significant? After adjusting for gender and age of the patient, donor age, donor sex, etc. Let us take 1 hour number of rejection episodes. That is what this. number of rejection. So adjust for number of rejection episodes, and you have a clear categorical variable for peak antibody level, age into 3 categories. Do the Cox proportional hazard model. Okay, shall we do it? So using SPS. Go to analyze survival, Cox regression, time is here, period, and the status. Okay. What is our important question? Question is this: peak antibody levels. There are 3 categories here. Okay. So categorical. Do you remember I spoke to you about dummy variable? Now I have 3 categories. One is less than 20, 20 to 30 or something like that, and so on. So here I need to say if somebody has less than 20 as the categorical, and the last category is the indicator variable, or the first category is the reference category. I need to tell the system. I'll take lower the value. That is the first category is my referral category. Indicator, see here I'm clicking those who had less than 20 antibodies as a reference category, and so I'm changing. Oh, sorry. So this is define an event and a categorical. Categorical, click here. So still it is there in the last category because I did not change it. Change this. Okay. Now this is anything else? So say sorry. Just go back to your analyze, survival, cog. I just wanted to put a few variables. Say for example, age of the patient, gender of the patient, whether he had a dialysis, yes or no. Age of the patient, age is categorized as 3 categories. I'll just maybe just age is as one variable. And whether he had a rejections, number of rejection episodes. What is my question? Did I put the question variable? Yes, peak antibody level is there. This is my primary question. I am adjusting for other risk variables and do the analysis. See the plots. Do you have log minus log S of t? This is what you need to ask for. So oh, hang on. Not that. Don't know why this is going. Were you able to run? Are you able to run in your machine? Do this one. Regression, transplant period, this, and only peak antibody level, and see whether it is not running in my machine. My system is hanging now. Just check whether you are able to run that one. It's running. Good. See, my machine is hanging. I don't know why. Okay, it runs now. Okay. Can you do this? Yes. Okay, so they get this output. How many times the hazard is more? So which one should I see? Where is hazard? E power beta is the hazard. Exponentiation of regression coefficient is the hazard. Here you see see here, this is your hazard. If someone had peak antibody level, and see this is this 2.9 times more. So did I say this is a categorical variable? Yeah, it has got two categories now. 21 to 80 is one group. If someone had 21 to 80 antibody levels, the risk of losing the graft is 3 times more. And it could be as low as 1.5 and as high as 5.7. We understand this after adjusting for age and gender. Yeah, this is category. Category. Zero, only two categories. I changed it. So the labeling that I have categorized as 21 to 80. Okay. two categories I had the data. So this is now the challenge is whether it follows proportionality assumption, the data. So what you have to do is just ask for, go back to this analysis, see whether it works. No, this is yeah, that is it's a bit tedious process to save the log minus log SFT values and then do some computing. Don't worry about it. So, but eventually it has to be done as log minus log SFT. Let's see how we can use it in R. Usually what we do is you save the log SFT, convert it into log SFT, do this whole process and plot manually the line. Don't worry about it. It's lengthy calculations. Now, are we ready? Shall we have a hands-on with the R software and see how we get to get the results in R software? Okay. Go to your this one, the PDF document. Take the PDF document. Go to Cox proportional hazard model. This is a Cox proportional hazard model. It's very simple. You have the ovarian data. Do you remember? Do you open it and copy this? What are the covariates here? The covariates are treatment and age. Data is ovarian, and summary we will put. Control C. I think your R is active still. Can you copy this one? The treatment, the exponentiation as a treatment provides a protective effect. 54% of the patients was protected as compared to the other treatment, and it is not statistically significant. Age is statistically significant, and so on. Can you do this Cox proportional hazard model? Do you have R code in? Can you please open your PDF file? Do you remember you had the ovarian data PDF file? Only copy the two lines, Cox, paste it in the editor and the R platform and run it. Is it okay? This is your regression coefficient. This is an anti-logarithm of it, e power of that regression coefficient, and standard error coefficients, that the p values. This gives you the confidence interval. Any questions? Hazard or relative risk or odds ratio, if it is less than 1, it is the intervention is protective, exposure is protective. Yeah. Similar to that, exactly similar to that. Instead of risk, we use risk ratio, we use hazard ratio. Yeah, exactly. The hazard is 3 times more as compared to this group. No, we should not use the word risk. No, hazard ratio. Hazard is 3 times. The ratio 3 times more. The hazard is 3 times more as compared to this thing. This is a continuous variable, age. So this is the yeah, correct. Yeah. This is a hazard ratio because the lower limit is 0.12 and the upper limit is 1.5. It should not have the 1 in between. Therefore, it is not statistically significant. Is that okay? So you can include many events, but you need to see how many events are available in your study data. The rule of thumb is 1:10. One variable, 10 bad events should be there. Yes, it's maintained here also. Yes, don't throw more variables into the model. Now, let us look at that PDF file. This is the diagnostic plot. So the diagnostic plot, we don't do that, the log minus log of S of t, but Schoenfeld diagnostic plot. We do this one. Let's see this, copy this and run it. I'll just copy this. This is so this is the plot which you have. If the blue line, you see here, the dotted blue line is nearly a straight line, parallel line to the x-axis, the assumption is met. So here this is the treatment, not so much, but but it's okay because this is, it should be linear. The blue color line should be linear. This is linear, but this is not linear. Okay, and that is how it's a very subjective statement. We need to see, how do I know the treatment follows violates the assumption or not, if I don't understand this one. I'll go back to my Kaplan-Meier survival curve and see how does the treatment behave. Can I do that? Do you remember we have done it for this variable? Now this is, the blue line has to be nearly a linear line to say that it follows the proportionality assumption, but it is not there. So this is, so what I have to do is just wanted to check whether it doesn't follow that assumption. I'll go to the R platform, minimize it and see. This is for treatment. This is Kaplan-Meier. Looks to me parallel. What do you think? They are touching each other. violating the assumption? Yeah. Schoenfeld residual says that it looks like it is violating the assumption. Okay. If you take the ratio of any time the 2 points may not be equal, that should be the concept. So do you understand this? A simple Kaplan-Meier says that it may not be a good variable to go into regression analysis. Yeah, I have to maintain the same distance everywhere. So here the problem is here that the distance is not so much. See here the distance, but here this, I don't know whether that is violating the assumption or not. So maybe I will not take a risk to put this variable into the analysis. That is the case. Okay. Now, simple Kaplan-Meier will help you to see whether we need to do this one or not. Now, I wanted you to take that, go to SPSS, read Anderson data, take Anderson data. Now, look at the analysis by Kaplan-Meier by gender. Read Anderson data by gender. what do? Would you put gender into the model? You will not put. This is Anderson data. So how do you handle it? Usually we spoke about this confounding. If there are two stratum, male and female, have a similar hazard, then you can stratify the analysis in Cox proportional hazard model. What do we mean by stratification? Stratification means you take the average of the two hazards and give you the results. But you won't get the results for gender. It gives you the results for the other two variables, log WBC and the treatment variable. Okay. When you have to do this procedure only when the two stratum risks or hazards are nearly similar. Adjustment. So when they are two different things, you should not use that option called stratum. Let me come back to this one. Say, for an example, my model is like this. My model is WBC treatment. Now I have realized that you people said don't put gender into the model. Remove that one. So can I adjust for it? The question is, can I adjust for it? Because it violates assumption. So when you say yes, somebody said, okay, you adjust for it, then I can put gender here. When am I ready to adjust for it? If male hazard is 3 and female hazard is 3.5 or whatever, close to each other, that time I can adjust for it. If there are two different values, don't ever adjust for it. Do the analysis separately for males and separately for females. Do you understand this? This is very, please remember, this is a very, very important concept. This is what we are going to discuss it in the afternoon also. Don't take it as granted that let me adjust for it because this serves like a confounder. Confounder means it has to be nearly similar to adjust for it. If there are two different values, don't adjust for it. Okay, when there are two different values means what? The male has 10 times the risk hazard and females have only 4 times the hazard, then don't adjust for it. Present it separate. When I say adjust for it, it will give you adjusted values for log WBC and treatment. You understand? So it will adjust for it. So this is, whenever you use this concept, the strata here in SPSS, adjusting for the variables which are violating the assumption has to be looked at very carefully in epidemiological perspectives. Whether when you say, are they nearly similar or different? That has to be understood. So many times into this concept, when you say adjust for the competing events, you put that one also. Don't ever do that. In the afternoon, we are going to do this. Okay. The question is, the adjusting is misused, and you have to be very careful if you want to be a good model writer. Okay. Now, any questions in the Cox proportional hazard model? I would say we have been teaching that Kaplan-Meier survival curves to see whether a particular variable is violating the assumption, instead of going for Schoenfeld residuals and things like that. But today, the science asks you the Schoenfeld residual analysis to check whether that assumption is met or not. Okay, I think you should know that there's something available there. And there are some codes that keep this codes, and be familiar with this one. With so CU statisticians will be able to help you in doing this codes if you get stuck with that. Any questions? We'll stop here. Then what we have discussed in the Kaplan-Meier analysis is that every time point we move ahead, we refined our denominator, isn't it? We removed the people who censored, who had a mortality, and removed from the denominator, and the probability changes. Because a conditional probability, we multiplied with the previous probability. It's a simple concept. The same concept which we are going to do in a different perspectives in the afternoon. Okay. And we need to understand thoroughly what kinds of model that we are going to use to do this analysis. Okay. There is a joke about surgery. Nobody is from surgery department. Anybody from surgery? Yes, no. So it should not be misunderstood. There was a tumor. Somebody was not well. He had a stomach problem. He went to a physician, and the physician examined and said, "You have a tumor. The prognosis is not going to be very good, so you should see a surgeon, a good surgeon." And we just meet with them. We went to the surgeon, and he also said, the physician said, "Low probability of survival is only 10%. What does it mean? If he operates 10 people, one will survive. He understood, patient understood, his probability of survival is 10%. So we went to the surgeon examined and said, that is true, your probability of survival is only 10%. But in your case, it is going to be 100%. Patient was very happy, but confused. He asked him, how about this 100%? Do you want to answer the question? He said, already I have operated 9 patients, all of them have died, because you are the only left two. So you have to survive. So whenever we say probability has to be interpreted very carefully. That is what we are going to see in the afternoon, how that the event confuses, multiple events confuses the probability interpretation.